let me define a function at Hn. Hn is the maximum of the first n terms of this function. Okay? So what? Say g1 and g2 and gn. Okay, so it's a maximum of first n functions of the sequence. My claim is that Hn for each n must also be in Fn. Okay? Must also be in Fn. And think about it. If this Hn is in F, so their integrals would be here.
So these integrals are over A. All these are.
I'm not specifying sets because that is going to show that I'm talking about a fixed set actually. Okay, you can keep it A, but treat A as an arbitrary thing actually. So it must be arbitrary. So yes, you can write A, it's fine. Okay?
Hence the sequence will be sequence of functions.
Yes. Which one? Hn?
We take the sequence of this integral.
No, this is the sequence of a number section that is converging to N. So that's a number. Okay? I'm saying Hn, which is the maximum of the first GNs. For each n, this must belongs to F actually. Okay? If this would be the case, then the integrals of Hn would be in this set. Okay? What would be the relationship between the integral of Hn and the integrals of Gn? Less than or equal. So there can be many things that you can conclude from it. So let's show that why this guy must be in Fn. So the first thing, is it measurable? That's an elementary exercise. You can show it inductively. Let's just show it for example n equal to 2 and then you can show it inductively. Let's show this for n equal to 2. Otherwise, let's take H2 because n equal to 1 would be trivial. So H2 would be the maximum of
G1.
G1, G2. Okay? And this is also, this was also an exercise where we did, what do you call, the chapter on measurable functions, that if you take the maximum of two functions and the minimum of two functions, it must be measurable. So it's a measurable thing. Since G1 and G2 are non-negative, so what?
The answer will be
They are also non-negative. So the only interesting property that we should prove is basically this property. Okay?
We want Hn to be
We want Hn to be
an F.
in F actually. Okay? So if I want Hn to be in F, I need to show that it must satisfy these properties. So that's measurability is obvious, non-negativity is obvious. The only thing that you need to show is basically this set. Okay? This inequality, this constraint must be satisfied. So in order to show that, consider a small set, really small, a simple set. It's a collection of the sets. So see, one of the trouble when you're going to integrate H2, in other words, you're going to integrate maximum of G1 as G2, is that the maximum of G1 and G2 is going to point-wise change its behavior actually. Sometimes G1 of x would be bigger than or equal to G2 and sometimes G2 of x will be bigger than or equal to G1. So okay, let's collect all those points for which G1 of x is less than or equal to or will be bigger than or equal to G2 of x. Okay? And then on complement you're going to have. So if you want to compute the integral of H2 d mu, what can I do? I can break it down into the two parts. I can say I'm going to have one part which is going to be A intersection B, H2 d mu, and other is going to be A intersection
B complement.
B complement and H2 d mu.
So this would be G1.
This must be, why it should be 0? Why should it be 0?
It's a G1.
So you're going to say that's H2. You're going to say this is same as G1 d mu A intersection B plus this is going to be G2 d mu A intersection B complement. Okay? So I would say, okay. You can also talk about, is this set B measurable? The answer is why it shouldn't be. So that's a number. So if you fix X, that's a number. Okay, since G1 is measurable,
So take G1 minus G2 greater than 0.
yes, you can also take in this manner. Okay, so that's a measurable set. So that means that A intersection B is a measurable set actually. Okay, and A intersection B complement is also a measurable set. So for this constraint must be satisfied not only for A but for A intersection B and A intersection B complement as well. Is it making sense? Okay. So I'm going to say that this is true because A is not fixed, it's an abstract A actually. So it could be A intersection B and A intersection, but it must be measurable. Obviously. So this must be less than or equal to nu of A intersection B plus nu of A intersection B complement actually, which is same as okay. That's it. That's what you need to prove, that H2 is in F actually. Agree? Okay. What essentially I want to do. Okay, so I can show inductively that say k functions are measurable, then if you add k plus 1, so it would be from the same argument you're going to get. So you can easily extend this for any k. Hence, by induction I can say, that Hn for all n. Can you see the trick that you want to play? What does this guy is doing? It's a very clever trick. So for G, I don't know whether it's increasing or decreasing sequence. I have no idea. Okay? But out of a sequence, okay, which satisfies the conditions there in F, he's constructing an increasing sequence. Okay? And the sequence is, it's increasing sequence. And it's kind of an increasing sequence which is going to increase to some function. So in other words, it's going to converge to some function basically. And whatever function to which this function would converge, that is your required f actually. Essentially, that's what you want. Are you getting the point? So out of Gn, which is not necessarily increasing, you constructed an increasing sequence, and you showed that that new increasing sequence has all these properties. So you are still, in the business, and once you are in the business, that's it. That's what you have to do. Okay. Now, why can I say that Hn must converge to something? In other words, point-wise, you can also say that point-wise. So can I say it's increasing? Is it bounded above?
Yes.
By what? Not necessarily. not necessarily. By the way, it is increasing. It's increasing to some function, which can take, or that function can explode as well actually. So you can have infinity, it could increase to infinity as well. But it, and it should be fine. So what I'm saying is that, okay, you define this new sequence, prove that this new sequence is an F, and let's assume that this sequence Hn is increasing to a measurable function F. Okay, it's increasing to a measurable function. That is non-negative and it has those properties. That is non-negative. Why is non-negative? Because all these are non-negative. Let's think still about it. Can I say for sure that this F, okay, so you can, so the only point that is going to be one of the troublemaking points would be that this sequence can diverge actually. It can diverge to what? Plus infinity. In that case, F would be plus infinity, but you can always find an F. Can I say in some sense that this F is always going to make sense? In other words, it's not going to explode. I don't see a reason. That why should I always assume F to be finite? It can take plus infinity value as well. Okay. Anyway. By the way, do you remember what is the meaning of increasing to a function F? So what does it mean that, H1, Hn is an increasing function and converging to that function? Okay?
So why this thing is, why it is increasing to some function?
If something is increasing and non-negative, so it must either converge to something, okay, some function, or in worst case diverge to positive infinity. That's it. So in worst case scenario, this would be, infinity, a function that gives you kind of infinity, or it could be the kind of a function that can give you finite values actually. Okay, so there is no restriction on F. Okay, so I'm not saying that, because if you want the finiteness of this, then you need upper bound. The question is, do we have an upper bound? No, we don't have. Anyway, so you have this. Okay, are we happy with this? Now, if this is the case, then I can run what is our monotone convergence theorem. Okay, I can run monotone convergence theorem. Why I can run monotone convergence theorem? By monotone convergence theorem, what can I say?
Non-negative
I can
increasing
say,
sequence.
okay, I'm sorry. Yes, I can say, so since Hns are in F, so I would say that this is same as, so the Hn d mu for the A are less than or equal to mu of A. And if you take the limit on both sides, okay, you're going to get H d mu, no, F d mu is less than or equal to
So mu of A, d mu of psi.
Yes. Mu of. Okay? What would be the last thing that we must show? That this must be the equality. Okay? So this inequality must be the equality. How can I consider, or how can I try to prove the equality? Is basically, for example, I can consider their difference. And somehow if I can show the difference must be always 0, then you're gonna have what you want. Okay. So the next thing is define a measure lambda of A that is the difference of mu of A minus the integral of f. Okay? This is what. Okay? What immediate thing you can say about lambda? Lambda must be a positive measure. It must be a positive measure. Okay? So now I would like to run, okay, so write it for example. Then lambda is positive measure for f in the set of. Okay?
For A.
Okay, f and A in A. Okay. For A in A. So that's. But if I want to say positive, it's just positive. That's it. Let's not get into it because positivity is not only restricted with one particular set. Okay, so it's a general notion. Anyway, so I defined what? I defined lambda of A to be the difference of mu of A and the integral. Now my claim is, or my intentions are to run previous example. The previous, what do you say, lemma, the last lemma, that said that if you have two finite positive measures, then they are either singular, or you can find an epsilon and a positive set such that the perturbed measure, is positive. Okay. Not positive, but the G is positive under that perturbed measure. Okay. So this is what that I would like to show. So what I would like to show, that the second possibility is not possible. In other words, the lambda and mu must be orthogonal, mutually singular to each other. Okay. So suppose lambda is not singular okay. Assume that lambda is not singular. Okay. So by the lemma, okay, there exists epsilon positive and a positive set G of a set, okay, set, measurable set G such that mu of G is positive. Okay, mu of G is positive and G is positive set under what? Under lambda minus epsilon mu 1. Okay. I'm going to show if this is true, you're going to have a contradiction. Okay. And how I'm going to show that? The L that I defined as a supremum of the set, I'm going to show that L will no more be a supremum. So I'm going to construct a similar kind of a element in F whose integral is bigger than L actually. Okay, that is going to be contradiction. In order to show this, consider any set A and consider mu of A minus integral A f dv. Okay? This is equal to what? This is equal to lambda of A. Okay? This is equal to lambda of A. And then can I say that this would be surely bigger than or equal to lambda of A intersection G? Because, A intersection G is a part of A. But then can I say that this is bigger than or equal to, because G is a positive set under this. So if I am going to operate lambda minus epsilon mu onto say A intersection G, then the lambda of A intersection G would be bigger than or equal to the epsilon times mu of A intersection G. So in other words, I can say that this is same as epsilon times mu of A intersection
G.
Agree? And then I can also write this as that this is equal to the integral over A of a function that is epsilon times the indicator function of G d. Agree? Alright? So what does this show? That this difference is bigger than or equal to this. By the way, what conclusion we can draw from here? Okay. So from the conclusion that I can draw from here is nu of A is bigger than or equal to F plus epsilon I G d. Can I say this? Just show this on the other side and combine the integrals you get that. And this also shows that this function epsilon plus I G belongs to the F factor. Okay? Now this is the troublemaking element. Can you see the trouble?
The integral.
Uh-huh.
The integral would cross L.
Yes, the integral of this is going to be for sure bigger than the integral of F factor. So what would be this? But I can say the integral over whole x, for example, of this function epsilon plus indicator function of g d mu would be equal to L plus epsilon mu of g. Can I say that? Because, okay, f d mu is what is, that's the L actually, the supremum to which, the things converge actually, okay? So this would be the case. And this number is strictly bigger than L actually. And that's a contradiction. So in other words, you found a function in F whose integral is strictly bigger than the supremum actually. So this means that this guy is not supremum. Hence, this cannot be true. Okay, so we're going to say that lambda is mutually singular to mu actually. Okay? And if the lambda is mutually singular to mu, what does it mean? It means I can find two sets which are disjoint and their union is entire x actually, so that you can decompose x into those two sets such that one has a measure 0 under lambda, another has a measure 0 under mu. Okay? So there exists a set H, okay, that is measurable such that, for example, mu of H has a measure 0 and lambda of H complement is going to be simply, I can precisely call it complement would be, what do you say, 0. But if this would be the case, what does it mean? This is going to denote hence, I will I'll say that what would be the lambda of h? The lambda of h is going to be nu of h minus h f du. Agree? This is 0. Okay? This is 0. So what does this mean? This means that nu of h, lambda of
H complement was 0.
okay. Okay. Just one thing. We haven't so far used anywhere at all that that mu is absolutely continuous with respect to mu actually. Okay? So one of the things that we're gonna see, let's little bit, let's just since mu is absolutely continuous with respect to mu, then nu of h is 0. Okay? And hence lambda of h complement. So if the lambda of h is 0, this is strange actually. What would be lambda of h? So we have lambda of h or h complement.
minus की जगह ना 1 minus 1. Lambda mu of h is 0, then mu of h complement is 1, then lambda of
1 cube of
Probability there for you.
probability value. Yeah. Okay, what you can say is that the lambda of h is going to be equal to the mu of entire x actually. Is it?
So this would also be 0 because mu is also 0 and mu of h is 0. So the integral of f would be 0, hence lambda would be 0. So if you compute lambda of h,
So what is the lambda of h?
it would be
mu of h.
Okay. उसकी वजह से 0.
Yes, sir.
So it's going to be mu of h minus the integral f h du, so this must be 0. Okay? So in other words, lambda is positive measure, but it's 0 actually. Okay? And if the lambda is 0, that's it. That's what you wanted actually. Okay? If the lambda is 0, what are you going to get? Now you can ask the question. Now you can say, okay, if the lambda of h is 0, why, okay, if the lambda of h is 0, then what would be the lambda of a actually, for any measurable set A? Because A is either going to be subset of h complement,
RH.
R is going to be h, R is going to be in both actually. So no matter what happens, it's 0 for all A and K actually. Okay? And hence I can say lambda is 0, so you got the inequality what you want. Therefore, the mu of A can be written as the integral A and FT.
You can say this
lambda of h.
mu of h, lambda of h is 0.
lambda of h 0 कैसे हुआ है समझ नहीं आया.
ये समझ समझ आया म्यू ऑफ एच एंड एफ डी यू एच
Yes, sir. By definition.
बाय डेफिनेशन.
Yes, sir.
अच्छा ठीक है हाँ ठीक देखें सो ठीक है म्यू ऑफ एच 0 है सो द म्यू ऑफ एच मस्ट बी 0 ठीक है